Have you ever noticed how kids love sticky things? Jam. Great for the hair. And great for sticking pages. Only adults hate stickiness. So the process of child rearing begins with training children to avoid getting sticky. There's a theory that adults dislike stickiness because it defies classification. What is this viscous gob? Is it a liquid? Is it a solid? Seems to be a little of both. In this program, we'll explore stuff that makes things stick together, glues. And if we can categorize glues, just maybe we'll rediscover the joys of stickiness. What makes glues stick in the first place? Is it chemical bonding or physical bonding? Why, for example, does a paper coaster stick to the bottom of a wet glass, but fail to adhere if the glass is dry? Both the glass made of silica and the paper made of cellulose contain a high proportion of oxygen atoms. This causes the dipolar water molecules to align themselves between the glass and paper, forming hydrogen bonds with both materials, which we will now call adherins. So, it is the intermolecular network of partial charges that holds the glass and paper together. At room temperature, this type of bond has considerable tensile or lifting strength. But it has very little shear strength. Slide the glass one way and the coaster the other, and they are easily separated. If the water is frozen, however, the coaster will be torn before it can be removed from the glass. But adhesives, which work only at sub-zero temperatures, aren't very practical. The challenge then for the adhesive industry is to develop room temperature glues, which hold up under the forces of stress. In order to form a strong bond, a mechanical interlock must exist. Most materials can be glued because their surfaces have microscopic fissures and indentations. These imperfections enable the adhesive, applied in liquid form, to penetrate the adherent, and after solidifying, interlock the surfaces mechanically. So a practical adhesive is one that is liquid at room temperature, but turns solid without cooling. The feat then is to change a liquid to a solid through a chemical process known as curing. And polymers are good candidates for curing. Polymerization can occur in the presence of any number of catalysts, metal ions, air, light, providing, of course, you have the right monomer. Let's examine crazy glue. The active ingredient in this fast-setting glue is cyanoacrylate. This monomer is a very thin liquid and easily penetrates the crevices of the adherent. When it makes contact with a weak alkaline solution, such as water moisture, which is present on most surfaces, it polymerizes at room temperature. Polymerization begins as the electrophilic carbon attacks one lone pair of electrons on the oxygen of the water molecule. The monomer then becomes a reactive species, and the chain reaction begins. In quick review. We began with a thin layer of liquid monomer, which in intimate contact with a thin layer of water quickly formed a hard glue interlocking two adherins. Now, if we apply the cyanoacrylate too thickly, polymerization will not bridge the gap. So, a little dab will do you. Not only should a glue form strong bonds very quickly, but it should also be able to resist chemical attack. As we know, pure hydrocarbon chains like polyethylene are not very chemically reactive. In the absence of electronegative atoms, they show effective resistance to moisture and most solvents. Polyethylene, then, would be a highly resistant glue, but not one with a lot of structural integrity. So a compromise must be struck. Adhesives must contain some electronegative atoms, trading off chemical inertness for tensile strength. A good example is the common polymer glue. When set, its structure is a three-dimensional lattice in which relatively high molecular weight molecules are cross-linked by strong chemical bonds. As well as these chemical bonds, hydrogen bonding holds the chains together and creates the required stiffness and strength. The compromise is that these same hydrogen bonds are vulnerable to chemical attack. Another potential weakness for a glue is thermal stress. When heat is applied, the atoms vibrate, weakening the hydrogen bonds and forcing the cross-linked structures to expand and unravel. As the temperature is lowered, the adhesive begins to stiffen again and solidify. For our purposes, the highest temperature at which a glue begins to solidify is called its glass transition temperature. Now, the more electronegative atoms in the polymer, the higher the glass transition temperature. Enter the hot melt adhesives, the majority of which are based on the ethylene vinyl acetate formula. This glue is solid at room temperature, but when heated above its glass transition temperature, it becomes fluid enough to penetrate surfaces and quickly resolidify. In its solid form, the glue comes in many sizes and shapes. From pellets to drum, it is fed to heating equipment, for which there are 10,000 industrial applications. So far, it has been implied that the adhesive should be stronger than the adherens, but this isn't always desirable. Pressure-sensitive adhesives, which have lower glass transition temperatures, peel away with just the right pressure. And let's not forget that one all-important characteristic: edibility. Boy, oh boy, we sure knew our polymers when we were little tykes.